The continuation of electric potential and the capacitance. Thus, you will be able to explain the principle of capacitors and their applications, and easily can derive an expression for the capacitance of parallel plate capacitor, and also you can obtain the equivalent capacitance of the combinations. Let us see in detail. Yes, now let us see electrical capacitance. See, the capacitance, which means the measure of the ability of the conductor to store the charges, right? Now, Q, that is charge, which is directly proportional to the potential. So, Q, which is equal to, we can say that CV. So, C is the proportionality constant and for the capacitance, right? So, we can say and write C, which is equal to Q by V. So, if V, which is equal to 1 volt, which means then C will be automatically, which is equal to Q, right? So, the capacitance of the capacitor, which is defined as the charge which is required to raise its potential through 1 unit. The SI unit of the capacitance is farad. The symbol which you are seeing on the screen, the 2 parallel lines should be there. And the capacitance is said to be, suppose 1 farad, which means we can say that the 1 coulomb of charge raised to potential of the conductor by 1 volt, right? Now, we can say that 1 coulomb of big amount of charges, the capacitance will be usually the ranging like millifarad, microfarad, nanofarad and picofarad, like that. Then let us see capacitance of an isolated spherical conductor, which you are seeing on the screen, that is the capacitance of the spherical conductor. Now, an isolated spherical conductor, which radius r we can take. So, the charge Q, which is uniformly distributed over its entire surface. So, it can be assumed that the concentric or concentrated center of the sphere, right? So, the potential at any point on the surface of the spherical conductor, we can say that V, which is equal to Q by 4 pi epsilon naught R. Okay, as we know that the capacitance of the spherical conductor situated in vacuum, which is C, which is equal to what is the value? Yes, Q by V. So, the value of V, which we applied here, we will get Q by 1 by 4 pi epsilon naught into Q by R. By simplifying this equation, we will get C value, which is equal to what? 4 pi epsilon naught R. Got it? So, this is the capacitance value for an isolated spherical conductor. And we can say that the capacitance of the spherical conductor, which is directly proportional to the R. From the equation itself, you can understand. And also, the above equation, which is for spheres, it may be the hollow or the solid spheres, it is applicable for it. And if the sphere is in a medium, then C value, which is what? C, which is equal to 4 pi epsilon naught, epsilon R, and small r, the radius we have to take it. Okay. So, 1 farad actually is very large unit of capacitance. So, it is not actually possible to have a single isolated conductor in a very large capacitance. The principle of capacitance. To know about the principle of capacitance, we know that very well. What is the electrical capacitance? So, this is the measure of the ability of the conductor to store the charges. Okay. So, that we can say that the capacitor, which means the arrangement of 2 capacitors which is separated by the insulated medium. So, that we can say that it's capacitor, and it helps to store the electrical energy or electric charge in it, right? That is only we can say. And before the slide also you have seen the symbol, right? The symbol for the capacitor, that is fixed mean it will be the straight parallel 2 lines. The variable capacitance also which is there. Now, what is the principle of the capacitance? See the first diagram, children. We can consider actually a positively charged metal plate A, and we can keep near the metal plate, the charged metal plate near one uncharged metal plate. Okay, close to that. Same like which is there on the diagram. So, due to the induction, the closer place of B, which acquires the negative charge, and it further phase acquires positive charge in the B plate. Okay, so the negative charge on plate B that tends to reduce the potential on plate A, while the positive charge on plate B, it helps to increase the potential on A. Got it? So, as the negative charge of plate B is closer to the plate A, then its positive charge will be get decreased. So A will get decreased some amount of potential, right? So obviously the capacitance will be increased by small amount. So this is the principle of the capacitance. In this way only it is due to the induction, the way only the charges are moving. So now if the positive phase of plate B is earthened, which means what will happen? Its positive charge gets neutralized due to the flow of charges from the earth. So this further reduce the potential on A and further it will increase the capacitance. By this way only step by step it is getting increased. The capacitance is getting increased. So this we can say that the capacitance of an isolated or insulated capacitor is considerably increasing when we place an earthened conductor near it. So this we can say that this system of two conductor we can say the capacitor. Now let us see the capacitance of parallel plate capacitor. See the capacitance of the capacitor, which means what? The charge which is required to be supplied to either of the conductors of the capacitor. So we can increase the potential difference between them, right, by unit amount. So that is only we said capacitance which is equal to Q by V. So this and all I am just given the gist and recalling the previous slides. You have to see again to know about the capacitance of the capacitor. Again you can recollect, right. So now we can move on to the capacitance of the parallel plate capacitor. Seeing on the screen that the parallel plate which we kept, right. So this is the simplest capacitor that we can say it consists of the two large plate parallel conducting plates and it is separated by the distance d. We kept the two plates separated by distance d. Got it? Now we can take A, which is the area, and the small d we have denoted there, that we can take it as the distance between the two plates, right. Now how to know about the capacitance of the parallel plate? See, first point we have to take the outer region. See, outer region which means we have to take the above the plate and below the lower plate. Got it? Above the upper plate we have to take it, above the lower plate we have to take it here, right. So what will happen? The electric fields due to the two charged plates will get cancelled out, so that the net field will be 0. So net field will be 0 means what will be come for the region of outer region E, which is equal to sigma by 2 epsilon naught, then minus sigma by 2 epsilon naught. So both will get cancelled out, 0 will come. So mathematically we proved. For the inner region, what will happen? So between the two capacitors plate in the inner region, you have to check the inner region, the lines which is charge density which is there, the electric field which is moving from one plate to another. There we can say the electric field due to the two charge plates will get added up there. So if that both will get added up means what is the base formula we said? E which is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught, which is equal to sigma by epsilon naught. Got it, children? So till that if you got it means we can move on to the next step. So that is the potential difference between the plates you must know. Then only we can easily know about the capacitance of the parallel plate. So potential difference between the plates, here the formula is what? Electric field into distance, ED. Okay. So electric field into distance between the plates we have to calculate. Then we will easily find out the potential difference. So V which is equal to ED. Then we are applying that value of the E here. What we find out? Yes, sigma by epsilon naught into D. So the capacitance of the parallel plate capacitor, what is the formula? Yes, all the three things which are interconnected with each other. You have to always check the previous slide. Then only you can easily know about the capacitance of the parallel capacitor. C which is equal to Q by V. Then the Q value and the V value we have to apply here. What will come the Q value and V value? Sigma A by sigma D by epsilon naught. Then the C value is what? A epsilon naught by D. So this is the capacitance of the parallel plate capacitor. What is the value for the parallel plate capacitor value? C which is equal to A epsilon naught by D. So from the equation we can say that the capacitance of the parallel plate capacitor which is directly proportional to the area, right? And this is inversely proportional to the distance separated by them. Got it, children? Yes. Now we'll see the series combination of the capacitors. See the diagram on the screen. The three capacitors of the capacitance C1, C2 and C3 which are connected in series, right? So potential difference V which is applied across the combination. So this sets up the charge plus q or minus q, whatever it may be, the plus or minus q on the two plates of each capacitor. Now, we can say for that the series combinations, which means we have to keep it in our mind, the charge is same in each capacitor. And we can say the potential distribution, the potential which is inversely proportional to the capacitance, so that we can take the potential V, which is equal to V1 plus V2 plus V3. So what is the base formula for that? V, which is equal to Q by C, as we know, right? We explained that. And so that we can take V1, which is equal to Q by C1, V2, which is equal to Q by C2, so V3, which is equal to Q by C3. So what we need? Q by C. So Q by C, obviously what will come? Q by C1 plus Q by C2 plus Q by C3. So we need the series combination of the capacitors. So the equivalent value 1 by C, which is equal to, or else we can say 1 by CS, which is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this we can say that the reciprocal of the effective capacitance is the sum of the reciprocals of the individual capacitance. Also we can say that the summation, right, 1 by C, which is equal to summation of I, which is equal to 1 to n number of capacitors when we connected. That is also we can say that 1 by Ci. Got it, children? Parallel combinations of capacitors. Right, the combination we have taken here the parallel way. See the diagram on the screen. The capacitors named, we have given the name C1, C2, C3 that are connected in parallel, and also the potential difference V is applied across the combinations, right? So now all the capacitors which have the common potential difference, right? So here we have to take the 2 point in that way of potential is same across each capacitor, but the charge distribution is directly proportional to the capacitance. Here, so we have to take the charges. So Q, which is equal to Q1 plus Q2 plus Q3. So we have taken here the base formula Q. So Q1, which is equal to C1V, Q2, which is equal to C2V, Q3, which is equal to C3V. So that the base formula is what we said, Q, which is equal to CV. So that we will get the final answer C for that effective capacitance C, which is equal to C1 plus C2 plus C3. So we can say that the effective capacitance is the sum of the individual capacitance. So this is for the parallel combinations of the capacitors. So what all we have learned from this video? The electrical capacitance, principle of capacitance, the capacitance of the parallel plate capacitor, series and the parallel combinations of capacitors. You may understand very clearly, children. Thank you, students.